Thank you very much. So first, I want to thank the organizers to give me this opportunity to speak here. So actually, I got to know Jean-Pierre a little bit when he was spending 3 months visiting in Peking University, where I formerly worked. Actually, we lived in the same courtyard, so we were neighbors, and since then we got a chance to talk a little bit. And I think he got especially happy when the secretaries there managed to arrange him to play table tennis in a local club. And I think he faced some like uphill game later, but he was pretty happy with that. So I think one of his main contributions to math is he basically improved the interaction between complex geometers and algebraic geometers. So today, my talk will be also along this line. So I will start to discuss one problem in differential geometry, and which I will draw an analogy later from the algebraic geometry viewpoint. So the problem is Kähler-Einstein problem for final variety. So I will continue the trend to talk about the final varieties, but I will go beyond the dimension 4. I think if you assume X to be final, and we start a metric such that the class of this metric is in the tangent, is in the C1 of this manifold, and then to study Kähler-Einstein problem, you look at the space of the metric, Kähler metric with the same class. So basically, you just look at the function f, smooth function such that so this is the space of Kähler metrics with the same class, and then there are basically 3 steps to understand whether there exists a Kähler-Einstein metric. So the first step is you basically set up a functional. For instance, there is this Mabuchi functional or Ding functional, such that the metric you search for is the minimizer of this function on this infinite dimensional space. Such that. So this is the first step. And the second step, of course, this space is not complete. So if you want to do analysis, you have to take some like a completion of this space. And depend on which analytic theory, you might take different completions, like a Sobolev space or the space of subharmonic functions with bounded energy. So anyway, you basically need to take a completion H bar which contain H, and you have to take the completion in a way that show MD can be extended to H bar. So then so once with this extension with the space to be complete, it's relatively easier to find the minimizer of this functional. But then you have to show that the minimizer is not just in this H bar space. It actually has to be in the original space. That's called a regularity. So basically, this is the strategy. Any question? So now I want to draw algebraic of this question. So we have to understand. So of course, we know that the corresponding algebraic notion is called K stability. This was originally defined by Tian, and it was put into algebraic geometry terms by Donaldson. So basically, their definition is if you look at the X, then you look at some objects called the test configuration. I'm not going to talk too much about this, but this is essentially just one parameter subgroup degeneration, polarized degeneration of this. And then you look at some invariants called the generalized Futaki invariant. You want it to be, you look at the psi, and you define the corresponding stability. I think we have to, let's say, okay, maybe let me just put it this way. So here, of course, the last one, you have to remove some like a trivial element. But except the trivial element, you want to be k-stable. You want it to be always positive. So the difficulty of this notion is you have to look at all the one-parameter subgroup degeneration of X. And how do you look for them? So basically, you look at your anti-canonic embedding. So you look at the embedding of X into Pm by larger and larger minus Rkx. And then you choose a C star inside of the PGL of this ambient space degeneration using Hilbert scheme. But one of the main difficulties is you have to choose R to be larger and larger. So a priori, there is no uniform R that you can just choose to there. So, but this was the more traditional viewpoint of this problem. So now we want to look at some development in the last decade. So the first thing is that we want to find some like a functional in some space. Here it's not clear how you put all this X into one space, right? I mean, as I said, you have to re-embed into larger and larger Pn, and it's hard to put them all in one space. But the following theorem by Fujita and Lee makes it possible. So this is called the Fujita-Lee criterion. So I would define the term later, but let me just say that, so X is K semi-stable if and only if that the notion of AXE is larger than SE for any E. I'll give the definition of these notions. And K stable, sorry, this is larger or equal to, if and only if. But you just replace this by any E. And now I put one more thing called uniformly K-stable. If the same inequality, but now you can allow some epsilon SE and E. And of course, the point is the epsilon is the epsilon is uniform, doesn't depend on choice of E. So what are the invariants here? So now here E is on some any divisor on some birational model. So E mapped to, so you can just regard it as a divisor valuation, but it lives above on some like birational model. And the AXE is called is the log discrepancy. So basically, if you compare the canonic class of Y plus E over X, and of course they only differ along some exceptional divisor because Y to X is birational, and you throw in one copy of every exceptional divisor, and then you get So basically, log distribution is defined this way. So basically, just the difference between kx and ky, and you look at the you correct them by 1, and that's log discrepancy. And for us, for people who know a little bit minimum program, know that we only consider so-called KOT singularities, which precisely means all these numbers are positive. So the AX is a positive number. So what's S? S is basically, if I have this birational model, I can assume Y to be normal or smooth. So I call this map mu. Then I integrate from 0 to of this number that the volume of mu upper star minus kx minus te and dt. And I will divide this by minus kx power to n. So maybe I write this too small. So I'll take the average over this. So I would like to write this as integral 0 to infinity, but of course, when the t is very large, when this is outside the pseudo-effective range, then this is 0. So basically, this is integral from 0 to pseudo-effective threshold, and you got such number. And this theorem tells you, by talking about k-stability, you don't need to look at the one-parameter degeneration. It's an if and only if condition, by just look at the valuation dividers. So now, if you look at this space, you think about this space as all the, if you look at consider all the divisor valuations, it plays a role like an edge, and then of course you want to complete it. I mean, depends on your viewpoint. I think, for instance, people like Berman, Buxton, Youngs, and they take a more non-Archimedean viewpoint. But for us, we just take the very natural completion is that we consider the space of all the valuations. But first I want to remove the trivial one for obvious reasons. So I don't want to consider the trivial valuation. And then I want to just put I mean, it's not necessary, but let me just say I want AX V to be less than infinity. I mean, the log discrepancy, I mean, you can easily extend, well, not easily, you can extend the function of this log discrepancy into the entire space of valuations. Then there are some objects may take infinity, but those don't matter with us. Is that on X? It's over X, on X maybe. Oh, that's right. Yeah, sorry, you're right. Thank you. It's a variation. So I look at this space, then I want to set up my function. Just by looking at this, you easily see the function I should set up should be A over S. By the way, S also can be extended to this space. So, and then since you want to study the ratio, and this is for adding E, so the natural thing I should study is the infirmary. So I define the X to be all the infirmary of this. You can either write E here or valuations. The infirmary are the same, so that doesn't matter. And then, of course, let's just say that it's k-semi-stable if and only if the delta X is larger or equal to 1. And uniformly k-stable if it's only larger than 1. But the k-stable one, so far, there is no, I mean, I will give you the theorem later, but that's the idea. But anyway, now let's finish our step A. We already set up the step A and B. We already set up a space, which is the variation space, and we set up we also set up the functional, which is this A over S. Now we want to start the minimizer. So basically our goal is to to understand the minimizer of A over S. So because you work in this complex space, there is a first theorem by Bloom-Janssen that the minimizer always exists. But their approach doesn't tell you too much about the geometry. So you don't know what, I mean, it's just one valuation. But I really want to this like a regularization process. So I want my minimizer to come from more geometrical perspective. Then two step. The second step is by Bloom, Liu, and myself is that the minimizers are cosine monomial. I mean, if you don't know what this are, it doesn't matter. I will talk about the definition when I state how we look and think about this. And the third step is by actually. Oh, sorry. Here I have to make an assumption that if delta x is less than the dimension plus 1 times dimension. I mean, I don't know whether this condition is needed, but as I said, we are mainly interested in the range between 0 and 1. Because if it's larger than 1, it's always uniform case stable. So we don't have to think about too much. So here, this is we have this technical assumption. And then we prove that the minimizers, okay, I should say there exists a divisor minimizer in the same range. And once you know the existence of divisor minimizer, it's not very hard to show that this minimizer indeed induces some special operation. So in other words, you have this kind of compactness type of result that I give you a final variety, there is an optimal dispersation. I mean, you might say, okay, actually, how about uniqueness? Indeed, this minimizer is not unique, but there is some way to modify the theory a little bit to even make it to be unique. So basically, putting all this together, it establishes a kind of a compactness theory for any final varieties without using GIT. And of course, for experts know that these two are related because this is kind of the picture what happens under the infinite place of this space. So somehow you have a minimizer under the infinite place tells you that there is a direction which is you have the most negative slope. So let me just state two theories of this, and then I will talk about a little bit of how we think about this kind of stuff. Oh, do it. Okay, so the first corollary, which is the one the analytical geometers care about, is that we know that X final, then K stability is equal to uniformly K stability. I mean, this is important because, I mean, it was a theorem by Berman, Buxton-Johnson, and Chile that this side is actually equivalent to the existence of at least a weak Kähler-Einstein metric even for singular final varieties. So you can extend the Yuchen conjecture from the smooth one to singular one, but the algebraic condition they use is this uniform K stability, whereas the original conjecture should be K stability, and we prove these two notions are the same. And the second one, which is more important to algebraic geometry, is so there is some object called the K moduli space. so this modular space parameterizes dimension n Fano with anti-canonical volume V. And I put a K here, means it's K moduli. And this modular space is proper. So if you know the first proof of the Yuchen conjecture, the smooth case by analytical people, I think one of the major challenges is this tensor partial estimate. I think first proof by Donaldson Sun is basically you have to show that when you take a sequence of Kähler-Einstein Fano manifolds, then the limit, the Gromov limit, is actually a Kähler-Einstein Fano variety. So in other words, the main challenge in there was to show that the space of Kähler-Einstein Fano varieties, even when you change the complex structure, it is actually compact. I mean, they managed to do this for the limit of smooth ones, but our theorem doesn't require this assumption. So from a high dimensional geometry viewpoint, if you study modular space of higher dimensional variety, the smooth bar assumption is not the right assumption because it's not an infinitesimal condition. There is no deformation theory attached to it. So somehow the right way you have to think about all the variety together, and then this give you the general points. Okay, so if you're interested in this kind of topic, I'm here and I'll be happy to talk to you. But now I will explain a little bit how we think about just come back to this question and how we think about this kind of thing. So one thing the thing is that if you want to take an approximation, here we define it as the infimum among all the dividers. But of course, it's better to find a subclass with more geometry and to say we can just study the limit by using those kind of subclass to approximate the minimizer. And that's what we first can do. So let me just make a definition. As I consider D, technically it's called a Q complement. I think this is some name from Shortcroft. But the definition is just easy. It's just say that D is the Q divisor. D is the Q divisor, which is linear equivalent to minus Kx, but it's Q divisor. So it might have fractional coefficients, whatever, and you require that XD is log canonic. So in other words, you add a boundary, make your final variety to be Kähler-Biot. So this pair now becomes log Kähler-Biot. And I will say E is an LC place of XD if it satisfies that AXE is equal to odd E, the variation order of E along D. So in other words, E is precisely the LC place of this pair. So if you do biological geometry, you know that studying this kind of divisor are extremely important. For instance, when it was used to all the induction of dimension in the study of minimal program. So then, what's nice about this E? So I will list several properties. So the first one, this property was basically from it's a consequence from BCHM, the Burke-Kashini-Hickman-Kerner result, is that there exists a Y. There exists Y, which extracts X, such that E is on Y, and the Y is a Maury dream space. Actually, you basically extract it to be a log Fano pair. So it's a Fano with boundary to be a KLT pair. But this is what we need. We need a Y is the Maury dream space. So one consequence from this is particularly that if I take the ring R to be the anti-canonic ring. So this is the coordinate ring for the anti-canonic embedding for X. Then, of course, I can define the gradient ring of R with respect to E. Right? I just look at the section, I look at the vanishing order, then I look at the order, vanishing order n, I divide by quotient by the space of vanishing order larger than n. That form of gradient ring. This gradient is finitely generated. This follows from the Morning-Dream space result. So this is the factor 1. Fact 2, I mean, that was proved in the paper with Bloom and Liu. We proved that at least when under the assumption. So from now on, I will always make this assumption, delta x is less than that. Because if it's too large, then we don't, I mean, it's already in our theory. We don't have to care about that. So I will remove this condition. So then I know that the delta is actually the infimum of AX EI of SX EI. So for all EI is like this. So we don't have to take the infimum among all the E. We just have to take a sequence of EI, which has this nice property, this LC place of some Q complement. And so this is not very hard to prove. I mean, once you know the theory well. But the next one is a deep result by Burka. So Burka theorem implies that there exists n which only depend on the dimension such that I actually can re-choose this D such that we may assume n kx plus di is true. Here, remember, it's not linear to 0. It's really linear equivalent to 0. For instance, that implies the coefficient of all the divisors is I mean, the denominator is divided by n. Whereas here, I just assume q, so you can just time any multiple. But here, n is uniform, such that, okay, sorry, maybe, let me just, and such that the x dr is still a q complement. So besides this, it still satisfies x dr is low canonic. So it still satisfies the same thing. Basically, you can replace d by di. And ei is a LC place of x di. So as I said, one of the major difficulties to understand K-stability is we have to go to larger and larger space of minus m. And at least that was how I think originally people think about this type of questions. But here, we want to still get this kind of boundedness result. But we take a different tool. So we first look at but instead of we look at the E to be bounded, we look at the complement. And the Burka theorem already provides you the boundedness on the base. So in other words, what Burka tells you that is this EI is actually a LC place of bounded family of divisor. Of course, this so particularly this implies that NDI is inside NKX. And this N doesn't depend on this I. It only depends on dimension. So the DI you look at is really just moving in a bounded family. So this is a step, first step, but that's not enough, right? I mean, you think about the 3 lines. All the weighted blow up is LC place. But of course, the weighted blow up, I mean, if you look at the embedding, it leaves like larger and larger embedding. So it's not in a fixed space. So, I'll talk a little bit how to overcome this later. But let me just say, the fourth observation is that this EI, this kind of EI, actually precisely corresponds to 1, correspond to the so-called weakly special test configuration. Let's say with irreducible special fiber. So, theorem definition by Donaldson, and he basically look at the stability by consider all the degenerations, and you have to study the static invariant. But as theory goes, we understand that we actually can concentrate on smaller class. And here, this is a class. I mean, for experts, let me just. This is a class that such that the test configuration together with the special fiber. First, the special fiber is reducible. This one is log canonical, and minus kx is polarization. So this is called the special. I mean, if you replace this by PLT, then it's special. But for now, we just know this EI is precisely correspond to this kind of weakly special test configuration. That actually draw a very direct bridge between the original test configuration theory and this kind of valuation theory. So, okay, now how to prove that B? So we kind of see this right. So we just, this moving a boundary family, this DI. So we may just assume DI is the same. I mean, if you move a boundary family, you can get a simultaneous logarithm is the inverse of progeneral type result. But all those results we already know. So that was already proved. So in other words, with this help of this kind of inverse progeneral type result, we know that we can assume D, let me just call it D infinity. So now I have this X, D infinity, and I take a logarithm of that. Let me just use another letter G. This is a logarithm. And then we know that the part, if I coefficient 1 is precisely the LC place. And then you can form a dual complex of this. This is just a dual complex. And then for each EI, so this dual complex is basically the slice of all the cone which computes place. Then every EI, basically after rescaling, it gives you 1 point inside this dg equal to 1, this dual complex. And you have an infinite amount of them. Of course, you just take a limit. So let me just say this is give me a point of vi, and then you just work a little bit more to show that this v infinity actually computes the delta invariant. But the bad thing about this is for divisorial valuation, it basically corresponds to the points inside this space with the rational coordinates. But here, when I take a limit, of course, I usually go out of the rational coordinates. I might just take a irrational coordinates. So I come back to show that there are rational coordinates to compute the minimizer. Oh, I cannot simultaneously move there. Cool. So we just continue our story. How do we get a rational guy? So was an old lemma by Chili and myself was this, that so this is Chili, is that if we know, I mean, of course, we can define the gradient ring the same way as for M valuation as for the divisor valuation. So if we know this ring, this ring is finite generated, then we actually know that in a neighborhood of V infinity, inside the minimal rational space containing it. But I can just assume with the minimal rational space, so I'm not going to write it down. So in a neighborhood of this, let's say this U, any V satisfy the gradient isomorphic to graded V infinity R. So in other words, the gradient ring structure is the same. You just change the grading a little bit. On one side, you can attach x to 1, y to 2. Also, you can attach x to pi. It's still the same space, the gradient ring. So, but this will immediately tell you that both the AX and SX are linear on U. But remember, A divided by S is minimizing until this point of V. But both A and S are linear in a neighborhood. That means in this entire neighborhood it's a minimizer, because otherwise it's not a proportional animal. So this will imply A V is equal to A V infinity, S V infinity. Because here I use the factor that V infinity minimize A divided by S. So of course, in the space, I have a lot of rational points which correspond to divisor valuation. So in other words, if I know the finite generation result, then I could be able to prove the minimal divisor. So now I want to proceed of how we think about this finite generation problem. So the theorem, as you can imagine, the first proof is given by, and then we have a second proof which works in more general setting by myself and Ziquan Zhuang, is that so again, let me just repeat this harmonious condition again. Then, if V minimize A divided by S, then GR is finite generated. So this is the finite generation result. So of course, as high dimensional geometers, if you want to prove something finite generation, you cannot just directly apply the condition. What minimizer tells you, that's we have no way to think about it. So we have to translate the condition into some birational geometry condition. So first, prove that the minimizer satisfies those birational geometry conditions. And then to prove those birational geometry conditions will imply the finite generation condition. So that's the business. So if you look at my A here, let's say that if E is a LC place of Q complement, then by BCHM it's finite generation. However, this is not true in higher rank. This was one of the problem, I think, obstacle the theory of at least for 1 or 2 years, is that the Arban, Zhuang, they actually found the example to say that there exists V, Fano, and D such that the D is Q complement. V is a LC place of XD. But V is not a divider. If it's divider, then BCH tells you it's a finite generation. But in that case, this is not a finite generated. Actually, you don't have to go to very deep, complicated X. So for instance, is equal to P2. So, but the D has to be the nodal curve, the nodal cubic. So if you take the other cubic, all the valuations are probably induced to finite generation ring. But this one is not. So somehow you really have to find the more sophisticated condition to imply the finite generation. And what I'm going to discuss next. So now I want to look back of this equivalence, especially 4 a little bit more. You know, in the 4, the right-hand side, this kind of weakly special test conversion, is not exactly the one we can basically put our class into the smallest one. So there is something called a special, and that's what we want to look at. So now let me just make a definition. So here, I will call this E is kind of weakly special place. But now I say E is a special place. I drop the word weakly special. Sometimes I call special LC place. There are 3 equivalent conditions. So the first condition is that E comes from a special test configuration. So if you don't know this, it's fine. I mean, basically, this is if you replace this by PLT. So in other words, the fiber is not just semi-canonical, it's really KLT. Then we call this special. But the other 2 characterization, the next one is such that if there exists an effective divider D, still Q divider, but now linear not to TKX, but to TKX, such that T is less than 1. So I can go down a little bit, and E is the only LC place of XD. So in other words, I can produce a PLT log final pair such that the divider is the only LC place. Of course, actually, you know, in a series of minimum program, usually it's their setting works. This, I mean, after you do like tie break, it's often this setting up is the way you make an induction. And here it's also our main hero in this. And but this one, it's not easy to generalize to higher dimension. So the third one is higher rank. The third one is the one I'm going to generate higher rank. Is there exists a Y mapped to X such that this E is the honest divider on Y. So it's not a valuation anymore. And there exists a dy. Again, exists dy on Y such that the round, so the only reduced part of the dy is E. Y dy is PLT. Again, we are in the DLT setting. And the third one you can imagine is this one is ample. So basically, I cook up a PLT final pair above, such that the E is inside the pair, and the X is the log final pair. The third one, I think you have a natural generalization to higher rank. So I can define what is a special valuation. So instead of a special divider, Now I call V is special over X. So I think I don't have else to make it to be symmetric. So if I just assume there exists the same as y over x and the dy on y, such that the first is minus ky minus dy is ample. So that's the last condition I stated. And the second is the pair y dy is, so the natural generation of PLT in high rank case is of course DLT. I mean, if you are experts, you like to make your life harder, you can call it QDLT, but it doesn't matter. I mean, I think DLT is enough. So let me just call it. But the last one is, if I look at the rundown, so if it's DLT, then the rundown is E, and the YE is going to be simple normal crossing at every generic point of the strata because the DLT condition. And I assume that V is cosine monomial with respect to this simple normal crossing. So here I basically remove all the locus where this is not simple normal crossing. So I just look at the simple normal crossing area, and the V is a cosine monomial over that. So this is called a special valuation. And the theorem. So okay, let me just put a very easy remark, is that because of this condition, then if I look at the dual complex of YE, this is a simplex. So this is a very easy argument following from any kind of Canadian theorem, you know. So then the theorem, so let me just call this simplex maybe C, okay. Then the theorem I prove with Zhuang is that if V, W are two values inside the interior of this, then the GRV is isomorphic to GRWR. No matter W are rational. For rational one, you just got to find generation from BCHN. But now you actually know that the irrational ones have the same gradient ring. The grade might be a little bit different. This isomorphic is just isomorphic as the abstract gradient ring. The grade, which is a real number, of course, depends on which valuation you choose. But so think about the toric case. And the second, of course, you have to show that the any minimizer under this technical condition, any minimizer is special. So if you prove this two together, then you just got to find generation. And I have a, sorry, that's my Trinity. I have 10 minutes left. So I will talk about some other settings. I will talk about other settings, which you can just apply the same sort of idea to think about things. I mean, you know, this is a pretty general scheme to study this type of problem. So I want to talk about two other settings. So if I start with the final variety, there is another thing called like an H function. So this is basically come from the Kähler-Rich flow. I think the analytical version was inspired by Perelman's work, but the algebraic version, I think it was first defined by Qi Li and Yuchen. So you study H functional. So basically, the property of this H functional is, if you look at if x is k semi-stable, then the H functional is minimized by trivial valuation. But if x is not, this is if and only if. So if x you start with is not k semi-stable, then there is some non-trivial functional minimizing it. And then if you apply the same kind of ideal, you know that basically this is a result by Bloom, Liu, myself, Zhuang, built on the earlier study by Qili and Han. So basically that we know there exists a minimizer. Actually, there is a unique minimizer. There is a unique minimizer of this H functional. So unlike the delta A over S case, this is really unique. And the second, that the GRV R is again the coordinate ring for the undercanonical embedding. This is finite generated. So this is the same as the A over delta case. And the third one is that if I study the degeneration from X, so let me just call this ring to be okay, let me just use this. Not give it a name. To this GRVR, this, let me just call it X. Oh, okay, let me just not give it a name. Then there is actually so because of this gradient, there is a torus action on that. And actually there is a vector attached to how you put the value inside R. So it's an abstract, the abstract gradient gives you the torus action. But how you put the gradient into R give you a Rabe vector. And you study this Rabe vector. So this thing, I mean, this is something called a modified K semi-stable. Or in our case, we just call it a K semi-stable. But it's not K semi-stable Fano. It's K semi-stable Fano together with a vector modified with respect to the H functional. And then you further degenerate this. You get some polystable object Y with the same Rabe vector. But this guy has a Kähler-Rich soliton. You know, if you study Kähler-Rich flow, you know the original, this was kind of proof for smooth one. You start with any smooth funnel, you run this like a Kähler-Rich flow, and this kind of Hamilton conjecture, which was later proved by people, that if you take the Gromov-Hausdorff limit of this sequence, if your X doesn't have a Kähler-Einstein metric, then this limit converge to some funnel variety with KR soliton. Here I'm just saying you can just forget every metric. You can just look at the underlying space, and this is what's happening in the underlying space. So and you don't have to assume any business. So KOT is enough, and is enough to give us a proper functor. So one more case which I'll discuss, then I'll stop. So another case is if I just consider the KOT singularity setting, the KOT singularity, and then the functional here is we study all the valuation which centered at this point. So now I'm not just considering the valuation. So this is all the valuations such that the center of this is equal to this small point. So this is called something called a non-commuting link. Then Qili defined. So I think it's always analytical people to help us to find the right function to work with. So Qili found that there is something called a normalized volume from this space to R and possibly infinity. And then there was something called a stable degeneration conjecture. Just say that, again, the same picture, that there exists a unique minimizer. But here, uniqueness up to rescaling. So basically, we know that if you rescale your valuation lambda by v by lambda v, it's the same thing. But that's only ambiguity. Second, that this is not generated. Okay, I should give some name here. The uniqueness was proved by Blue, not Bloom, by myself with Zhuang. The uniqueness was proved by Bloom first. And then this finite generation was proved by myself and Zhuang. And so the third one is, this was known before we know the finite generation. So we assume the finite generation. Then that if I study the singularity, now I degenerate to spec, not the approach, the spec of the gradient ring. Again, with the Rib vector. Then again, this is K semi-stable. But now this is the K semi-stable in the log final cone case. It captures the Sasaki-Einstein metric. So this one is Kähler-Richie-Soliton. That one is minimizing the Kähler-Einstein. Here, this is Sasaki-Einstein. And then again, this is degenerate to something which was Sasaki-Einstein metric. Or actually, for the singularity, maybe I should say Ricci-flat cone metric. It's a link has a Sasaki-Einstein metric, and it's if and only if. Again, you have this kind of setting. The algebra. I think again, this was known in the singularity coming from the limit of smooth Kähler-Einstein manifolds. That was done by Donaldson and Sun, but there is an entirely general geometry picture behind. So the last thing I want to mention is, so basically, I think this theorem gave a pretty good understanding of the finite generation in the case if you want to degenerate to something which is KLT. But in the divisorial case, we actually understand that it is degenerate to something which is semi-long canonically irreducible. But in the higher rank case, we have no such result yet. So I think it would be nice to fill in the gap of how we understand the, what is the birational geometry condition to characterize the finite degeneration with possibly semi-LC irreducible degeneration. That's one direction. The second direction is, if you look at the dual complex, then I ask myself, how the special valuation, or even finite generative one, are distributed among all this valuation space. So BCHM tells you the rational one are all so then that may not be a good result. So a good picture. So a good picture, I think you really have to ask the special one. Then whether there is kind of like a cone theorem type, like there is some like a finite, not the local polyhedron, but close to local polyhedron picture to characterize the special one. We also don't have an idea of that direction. Okay, I'll stop here. Thank you very much.